Welcome back everybody. This is our 14th class in JEE mains previous year questions for chapter current electricity. Before this video, we have made 13 videos in this series and all of those videos are available on our YouTube channel. Name of channel is Point Basics and there is a dedicated playlist for this type of videos. We have also started similar playlist for NEET previous years. So if some of your fellow friends or classmates are preparing for NEET, you can suggest them that playlist, and that playlist can easily be found on our YouTube channel's playlist section again. And if you like these videos, then do press the like button, share them as much as possible, and subscribe to our channel. It would be a great help. Share and subscribe. Also, if you want to support us financially, then you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Even a small help will be highly appreciated. So with this, let's start today's video. And in previous video, I think we covered up to 116. Let me scroll. Okay, this is 170. Okay, so today we will start with question number 180. So let's slide it on the left side and adjust pen thickness. Now, as per question, in a meter bridge, a wire of length 1 meter has a non-uniform cross-section such that variation of its resistance with length is. So here you can see down here in the diagram that cross-section of wire is not uniform, and actually its radius, I think, is increasing. The wire is of conical shape and its radius is keep on increasing as we move, and due to increase in radius there is variation in distance, there is variation in resistance. So as length is increasing, resistance is decreasing. So as we know that when area increases, resistance, as length is increasing, with length its cross section, as visible from the diagram, cross section is increasing. So as a whole, resistance is also decreasing. But we what we have to use, we have to use this formula as mentioned here. We will use this formula to find out, we can say, a relationship between resistance and length. Now the galvanometer shows zero deflection when jockey is at point P. What is the length AP? So as galvanometer or this whole circuit is in balance condition, then according to balance condition of a Wheatstone Wheatstone principle, we can say R dash, this R dash by L should be equal to R dash by 1 minus L. Or in short, we can write that, yes, okay, wait a minute. This was for normal Wheatstone. This is for normal Wheatstone bridge, where wire cross section is uniform. But in this case, we don't have uniform cross section. So what we will have, we will have R dash divided by resistance up to length L is equal to R dash resistance of the remaining part 1 minus L. So R dash get cancelled from both of sides, and from this, resistance up to L length should be equal to resistance of the remaining part. So this is the relation here we have. Now writing this formula, that relation which is given to us, dr by dl is proportional to 1 by root L. We can remove proportionality by adding some proportionality constant. So dr by dl is equal to k by root L, and adjusting the variables, dr should be equal to k times 1 by root L into dl. Now we will integrate it up to length L, and then we will integrate it to up to length 1 minus L, because we have to find the resistance of both of these parts. So integrate between limits a to b, and here we will have r of, so here we are integrating between a to b, means we are just taking here resistance from starting point A to ending point B. So here we will write resistance from A to B will be equal to integral of this whole will give us 2k into root L with limits A to B. Now first we will find resistance for L and then for the remaining part. So for up to length L, what we do, we will find resistance, we will start from 0 and go up to L. So resistance up to length L will be 2k root L limits 0 to L, and that will be just equal to 2k root L. Now resistance of the remaining part means 1 minus L. For that, what we have to do, 2k root L. Now limits will be starting from the L and limit will go up to 1. These will be the limits for resistance of the remaining part. So lower limit will be L and upper limit will be 1. So what we will get, 2k into root of 1, that is 1, minus root of L. So these will be the two value of two resistances, and as per our initial condition that both of these resistance should be equal, so 2k root L is equal to this value, and it is equal to 2k minus 2k root L. Adding these two, and we will get 4k root L is equal to 2k, and from this k get cancelled, and we get root L is equal to 1 by 2, and squaring both of these, both sides, L is equal to 1 by 4. And as we know that it is in meters, the length is in meter, so it is 1 by 4 meter or 0.25 meter or 25 centimeter. Option C will be the right answer. Moving to the next one. A ideal battery of 4 volt and resistance are connected in series in a primary circuit of a potentiometer of length 1 meter and resistance 5 ohm. The value of R to give potential difference 5 millivolt across 10 centimeter of the potentiometer wire is. So we have been given potential and some resistance R and a wire of length 1 meter with resistance 5 ohm. So total current or total resistance of the circuit will be resistance R plus resistance of the wire, that is 5 ohm, and current in the circuit will be battery potential, that is 4 by total resistance R by 5. So this will be the current flowing through the wire. Now it is mentioned that we need to adjust R such that potential difference of 5 millivolt across 10 centimeter of the wire. Now suppose this is our wire, the wire AB of length, suppose one that is 100 centimeter. Now as also wire also have some resistance, and its resistance is mentioned already, that resistance of wire is 5 ohm, and suppose VAB is the voltage across it. So VAB is the voltage across the wire. So voltage drop per centimeter will be VAB by 100. This will be the voltage drop per centimeter of the wire, and it is mentioned that in 10 centimeter, this voltage drop should be 5 millivolt or 5 into 10 raised to power minus 3. Now adjusting these values, what we will get, we get VAB means potential across the wire, that is equal to 5 into 10 raised to power minus 2 volts. So potential produced across this wire is 5 into 10 raised to power minus 2 volts. Now we know that resistance of wire is 5 ohm. So resistance of wire is 5 ohm. So using these two values, we can find out current through this wire. But we can find current through this wire, and current through wire will be potential by resistance. So that will be 5 into 10 raised to power minus 2 divided by 5. That is resistance of the wire, that is 10 raised to power minus 2. Now current of the circuit is given by this, and current of the wire is given by this value. And as this is a series circuit, so circuit's current should also equal to current of the wire. So we can compare both of these and we will get the final answer. So 4 by R plus 5 is equal to 10 raised to power minus 2 or 1 by 100. Solving this, R plus 5 is equal to 400, and from this R is equal to 395 ohm. That is option C. Now moving to the next one. The resistance of a meter bridge AB given in the figure is 4 ohm with the cell of EMF E is equal to 0.5 volt and rheostat resistance RH is equal to 2 ohm. So this resistance value is 2 ohm and EMF is 0.5 volt. This is 0.5 volts and meter bridge resistance, so we can say RAB is 4 ohm. So this value is done, this is done, and this is done. A null point is obtained at some point J, somewhere between we obtained the null point. When the cell is replaced by another cell of E is equal to E2, the same null point J is found for RH is equal to 6 ohm. The EMF E2 is. So here we have two scenarios. In first scenario, we have a cell of EMF E which is balanced at point J. Now in second scenario, we replace this cell with EMF of E2 and we also replace this rheostat with resistance of 6 ohm, and now balancing point is same for both of these. And if balancing point is same, then what we can do, we will first do calculations for the first cell and then for the second E2 cell, and then we will compare both of these. Now we know that at the null point, when system is in null point, there is no current flowing through the measuring cell. Which one? As we are measuring using this cell, this part of the circuit, is our actual Wheatstone bridge. This lower part of the circuit is actual Wheatstone bridge, and upper part is the measuring cell using which we are finding value of E or E2. So in the upper part, when system is null point, in the upper part there will be no flow of current, and in the lower part, when system is in a null point, there will be a flow of current. So first of all, what we will do, for the first case, we can say case 1. For case 1, we have E is equal to 0.5 volt and RH is equal to 2 ohm. Now current in the lower part, or we can say IAB. This is IAB. IAB will be total potential in the lower circuit, that is 6 volt, and total resistance 2 ohm from the rheostat and 4 ohm from the wire. So it will be 6 by 4 plus 2, 6. So 6 by 4 plus 2, that will be 1 ampere. Now, as we know that this cell E is now at null point when this galvanometer is connected at point J. So potential across V potential across A and J point should be equal to potential of this cell. So we can say VAJ should be equal to E, and that is equal to 0.5 volts. Now coming to VAJ, how we will find VAJ? We can find VAJ by just current into resistance of AJ. If we can find resistance of A to G, or resistance of the wire from point A to up to point J, then we can just multiply it with the value of current and we will get VAJ, that is equal to E, and that is equal to 0.5. Now how we will find the resistance of up to AJ? We know that resistance of wire AB is 4 ohm, and assuming this whole wire is of 1 meter or 2 meter, whatever you can assume, just keep that value constant throughout the question. We are assuming that length of wire is 1 meter. So if length of wire is 1 meter, then this 4 ohm is divided across 1 meter, and we have length, suppose we can say this AJ length is equal to L. So resistance of this L part will be, value of I we know, that is 1, and 4 ohm is divided across 1 meter and into L, that is the length of AJ, should be equal to 0.5, and from this we can find out that L is equal to 5.5 by 4. 0.5 by 4. Now coming to case 2. Now in case 2, what we have? E is equal to E2, so we don't know value of E2, and RH is equal to 6 ohm, and balancing length is same. So balancing length is again L, and initially it was also L. So in this case again, there will be balancing and no current will be flowing in the upper circuit, but in the lower circuit there will be current, and we again can say that V of AJ should be equal to E2, and V of AJ again will be equal to I times RJ. Now value of I will change here. It is I times RAJ is equal to E2. Now value of I will change because the value of rheostat, which was previously 2 ohm, now it is 6 ohm. So value of I will become 6 by 6 plus 4. So 6 by 6 plus 4, and now RJ will be again 4 divided by 1 into length L, and length L is 0.5 by 4. So 0.5 by 4 is equal to E2. So this get cancelled, and this is 6 by 10, and multiply 5 by 10 is equal to E2, that is 30 by 100 or 0.3 volts. So option B will be the right answer. Let's move to next question. In a Wheatstone bridge, as per shown in the figure, resistance P and Q are approximately equal. P and Q are approximately equal. When R is 400 ohm, bridge is balanced. On interchanging P and Q, the value of R for balance is 400 and 405 ohms. The value of X is close to. So we have to find out value of X. So as for the conditions for this question, that P is approximately equal to Q. This is what we have been given. And for the balance condition, in this scenario, we will have P by R is equal to Q by X. And bridge is balanced when R is 400 ohm. So value of R is given, and R is equal to 400. So we can say P by 400, and we have to find out value of X. So equals to Q by X, and from this we can say X is equal to x is equal to 400 q by p. This is the value of x. Now this was initial case. Now interchanging will happen. Interchanging of p and q. Now p and q are interchanged, so means here we have q and here we have p. And now bridge is balanced for value of r 405. So in this condition, balance condition will be, in second scenario, balance condition will be q by r should be equal to p by x, and now value of r is 405. So q by 405 is equal to p by x, and now x will be 405 p by q. Now as we have not changed value of x in both of the cases, so these two values should be equal. These two values should be equal, and equating both of these, 400 q by p should be equal to 400 p by q, and from this we can say p square by q square is equal to 400 by 405, and now what we can do, we can find out value of p by q is equal to under root of 400 by 5, and here we have to find value of x by q by p to find the value of x. So q by p will be equal to under root of 405 by 400, and solving this we get 1.006. So now value of q from this equation, value of x from this equation, so x will be 400 times q by p, and q by p is 1.006, and solving this, multiplying, we get 40.2.5, and option D is the right answer. Moving to the next one. In an experiment setup of a meter bridge shown in the figure, the null point obtained at distance of 40 centimeter from A. So this is 40 centimeter for the first case. If a 10 ohm resistance is connected parallel with R1, so here we will connect a 10 ohm resistance. The resistance that should be connected in parallel with if 10 ohm resistance connected in parallel with R1, the null point shift by 10 centimeter. The resistance that should be connected in parallel with R1 plus 10 such that null point shift back to initial position. So in this question, it is mentioned that initially we had balance condition with R1 and R2 with R1 by 40 is equal to R2 by 60. And from this we can write R1 by R2 is equal to 2 by 3. Now what we done, that we connected a 10 ohm resistance here in parallel, not series, sorry. With R1 resistance we connected a 10 ohm resistance in series. So let me change this. So this will be our modified circuit, that we have R1 and 10 ohm resistance with series. This is R1 and this is 10 ohm in series. Now point shift by, our null point shift by 10 centimeter. Now what we have to do, we have to again attach a parallel resistance here so that it again comes back to 40 centimeter, and value of this we have to find out. Now suppose value of this is x, Now, if this whole pink circuit, if this whole circuit give us back the value of R1, then we will get again 40 centimeter balancing length, because initially there was only R1 resistance and it was giving balancing at 40 centimeter. Then we added 10 ohm to series, and then we also added, we can say, a X resistance in parallel, and we again come back to 40 centimeter balancing length. Means this whole circuit is equal to R1. The series combination of this whole circuit, or we can say total net combination of this whole circuit, is equal to R1. So combination of this whole, or final resistance of this whole combination, will be, here we have R1 and 10 in series and X in parallel, so their total resistance will be equal to 1 by X plus 1 by R1 plus 10, and we can take here LCM. X R1 plus 10, here we will have R1 plus 10 plus X, so this is 1 by RT. So from this, RT is equal to X R1 plus 10 divided by R1 plus 10 plus X, and that should be equal to R1, because we are again going to our original balancing length. So let's see if we can solve using this method. So from upper part we will get X R1 plus X, or 10 times X, and from lower part we get R1 square plus 10 R1 plus R1X. So no, we are getting a quadratic equation here, so we will have to use the another method, or the, we can say, second condition which we have to use, that balancing shifts by 10 centimeter if R1 is, if 10 ohm resistance is added in the series. So let's rub this, or we can say let's start from the scratch. So initially we had R1 by R2 is equal to 40 by 60, or 2 by 3. Now what we did, we added R1 plus 10 ohm in series, so R1 plus 10, and now balance point shifts by 10 centimeter. Now as we know that resistance on this side, on the left side, is increased, so balance point should go towards the right side. So initial balance point was 40 centimeter and it shift by 10 centimeter, so it becomes 50 centimeter now, because resistance on the left side is increased, so balance point will move towards the right side. So now in the second balance condition, R1 plus 10 by R2 is equal to 50 by 50, that is equal to 1. So R1 plus 10 is equal to R2, and we have another equation here. So if we can put value of R2 here, R1 by R1 plus 10 is equal to 2 by 3. 3R1 is equal to 2R1 plus 20, and from this R1 is equal to 20 ohm, R1 is equal to 20 ohm, and R2 is equal to 30 ohm. Now we will use that condition, that if we add some resistance parallel X here, its combination of this whole circuit will be equal to R1. So now combination of this whole circuit, as we know value of R1 is 20, so we will write it 20. So 20 and 10 in series will give us 30 ohm, and total resistance of this whole parallel circuit will be 1 by RT is equal to 1 by 30 plus 1 by X, and that should be equal to 30X into X plus 30. So RT is equal to 30X by X plus 30, and that should be equal to initial value of R1, because we are switching back to our original length. So resistance should be also equal to original resistance, that is equal to R1, and R1 is 20 ohm. So R1 is 20, and using this 30X is equal to 20X into 20 into 30, 600. So 10x is equal to 600 or x is equal to 60 ohm. So option C will be the final answer here. And with this, we end this video here. Hopefully, whatever we have covered here will be helpful and useful to you. Again, if you find this video useful, helpful, do press the like button, share this video as much as possible, and subscribe to our channel. Also, if you want to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. Any help will be highly appreciated. So with this, again, thanks for watching, and we will meet in next video.